Hi, I wanted to take a look at a problem with a car and a barrier. This is a little bit different than what we've seen. I don't think I gave you a homework assignment problem with this, but this is a good one to look at. Um, so this one is, and this is one of our exam applications I had mentioned at the beginning of the chapter last time. So you have a car, and you're designing, you want to design a barrel barrier for a car. So if a car to protect if a car went off course and struck was on the way to strike a certain fixed structure, you can have a barrel barrier to protect it. Now, with this particular barrel barrier, what you would find, or with a barrel barrier, you'd find that the force being applied against a vehicle or something that hit it would be a function of position. Okay. Now, in this example, we have an equation representing it, essentially, and this is the force as a function of position. Okay, and this one is where we have x is in feet, and we want to determine how far in it's going to push the barrier before the car comes to a stop. Okay, so this is in the section of energy, work and energy. So we have the work and energy equation. So our governing equation really for this one is just our work and energy equation. So it's just whatever initial energy the car has, whatever work is done against the car, we're going to have some final energy associated with it. Okay. Now, in this case, what we're dealing with is the kinetic energy of the car. So T1 is whatever kinetic energy the car has initially, or at least when it strikes the barrier. Here's the work of the barrier against the car, and the final kinetic energy. Well, the assumption here, of course, is that the velocity has stopped, so the car has no kinetic energy at the end. So all of it, all the energy, initial kinetic energy, T1, has been converted to basically deform the barrels or crush the barrels, having work done on the barrels. Okay, so this really gets us back to this part of the equation, just in terms of the work form. If you remember from previously, um, the work equation could just be basically, the vector force um, dotted with the incremental component of the displacement, the vector displacement. And it's from whatever position it originally was to a vector position in the final position. Okay. Now, when we looked at it in terms of like tangential force, we could actually simplify it, or we could actually simplify it in this form because we really only care about the force that's tangential to its motion. Okay. So here's the form. So here would be like here's like the initial position, and here's the final position. Here's the force, and then the angle. Well, in our case, there's no angle. It's right along the forces of the acting on the car is really just against the car, directly against it. So this actually, the angle 0, so this comes out to be 1. So the form of this really is just, here's the summation of all of the work, which is just going to be equal to, against the car, it's just going to be equal to whatever displacement is initially to the final displacement. Okay. And actually, this just simplifies to just work from 1 to 2. So there's really only one component. All right. So for this problem, what we what we find is that we have some initial kinetic energy, and here's our equation for kinetic energy, initially, and our final kinetic energy. Okay. So let me just continue on here. So if I go and substitute in for that, I have what I'm going to have is here's my initial displacement of the barrier, right, which was 0, out to its maximum displacement. So all I do is substitute in for, and now you're going to use x because it's in the x direction. S is just in the x direction, so I can use that. And here's my equation for the force. Okay. Of course, here's the form of the integral that we'll find. And so if I perform the integration completely, the closed form, this is what I have. Minus 60 times 10 to the third times x max raised to the third half power. Right? Now if I go through and do the calculation for T1, T1 is just going to be equal to 1 half, and here's the mass times its velocity squared. And it's going to be 349 times 10 to the third foot-pounds. Okay, so that's my initial um, kinetic energy associated with it. Okay. Well, I could just take that initial equation. If I go back, here's my initial equation. I just take and put this over into the other side of the equation. I'm going to have T1 is equal to the negative of this, essentially. Okay. And of course, it has a negative sign in it, so those two negative signs cancel out. All right. So when I do that, I divide both sides by, so I have this on one side, and this is also equal to T1. So it's the negative of this, negative, negative. So it's 60 times 10 to the 3, I max, x max raised to the 3/2 power is equal to this. Okay, so this is the other side of the equation, all right? So all I do is divide both sides by 60 times 10 to the third pounds, and then that cancels the pounds, and we're left with just 5x max raised to the 3/3 power is just 5.81 feet. If I do both sides to the 2/3 power, I come up with the final result, which was 3.23 feet. Okay, and just real briefly to show you in terms of the solution set, the author's solution, which kind of skips some points. But basic idea is that, you have the negative sign here. Here's my T1. Here's the summation of all the work going from position 1 to 2. Here's my integral, okay, that I showed you. Here's my mass, so 1/2 mv squared minus this, because it's a negative sign because it's in the opposite direction of, see, here's FB, force of the barrier. It's in the opposite direction of the motion of the car. Okay, so as I showed you, going through and solving for that, you'll come up with 3.24 feet for that when you go and perform the integral. And that's it.